Okay, for this last section, we're going to be looking at what is the calculus of polar curves. So for this section, you're going to see when you look at the problems, it's kind of ideal that if we have polar equations, that we can have them in function form where r is by itself. So like r is the dependent variable, theta is the independent variable, so r depends on theta. So if you look right here, ooh, look at that. R equals f of theta. So that just means r is by itself, the other side just has the angle in it. Now think about it. Why is dr d theta not the slope of the tangent line? Because r being the radius, theta being the angle, dr d theta would be the rate that the radius changes for a momentary change in theta. So, we could have a specific angle, and we could denote how fast the radius is changing at that moment. But what we often want to know is if we're modeling something in polar form, it's still graphed on a Cartesian plane. And so we want to know, well, what will the tangent line be? What's the direction of the force, or what's the direction of the motion there? And so dr d theta won't do that. Now, to get dy dx, sorry, the slope of the tangent line, it's actually not all that tough. All right, and so the focus would be, let's suppose we have an r equals f of theta. Well, if you think about our conversions, one of our conversions is x equals r cosine theta. The other one that we can use a lot, y equals r sine theta. So if we want dy dx, we really just want the derivative of y over the derivative of x. Now, but we don't want r's, right? We want r by itself, so we want thetas. Well, if r equals f of theta, I can do a little substitution here. I can say that x is equal to f of theta times cosine theta, and y is equal to f of theta sine theta. Well, I can find dx d theta. And I would do that using the product rule. It would be the first, f of theta, times the second, times the derivative of the second, negative sine theta, plus the second cosine theta, times the derivative of the first, f prime theta. I can also find dy d theta. Again, using the product rule over here. Here. No, not there. Here. There we go. So, for dy d theta, it'd be first, f of theta, times the derivative of the second. The derivative of sine is cosine. That's a theta. Cosine theta. Plus the second, sine theta, times the derivative of the first, f prime theta. Now, just like with parametrics, if we have dy dt and we have dx dt, we really have dy dx because we can put them over top of each other. Same thing here. If we have dy d theta, and we put that over dx d theta, we flip, multiply, and we are left with dy dx. So that thing I've got here, put it in fraction form, dy over dx, and you get what is on the next page. So here at the top, I've got the dy dx formula, f prime theta sine theta plus f of theta cosine theta over f prime theta cosine theta minus f theta sine theta. Now, of course, that's something that you would want to know, need to know, and it's something to memorize, but think about where it comes from. Okay, it comes from the converters. The fact that x equals r theta, y equals r sine theta, x equals r cosine theta, y equals r sine theta. R is just the function form, r equals f of theta. And then we plug in and take the derivative of each separately, put it in dy dx form. So there's your formula. Now, the focus of the video here is really going to be just to make sure you have the essential formulas. So I've got the rest listed on this slide. So we've got area. Now, area, when you think about a polar curve, what does that mean? Because we're a little bit different than like between the graph and the x-axis. Area with a polar curve means between it and the origin. So we haven't dove too deep into some of the graphs, but you can have some graphs that one's called a cardioid. It looks kind of like that. When we do this area formula, what we're getting is the area between the graph and the origin is what it is. And so the A and B are really an alpha and a beta here, your limits of integration. They are angles. So they're angles for your limits of integration. I know they're angles because I see d theta. And remember, everything should match variable-wise. So d theta means everything's in terms of theta. Now you might say, well, what the heck's this r doing in here then? Well, that's because r equals f of theta. So you might have, for example, r equals 3 cosine theta perhaps. And so that r gets replaced with the formula 3 cosine theta. Same thing for the derivative up here. F of theta, that's really the derivative, that's really like the 3 cosine theta that's over here. Well, anyway, I'll leave that. I won't clear it up. But the second formula there is area between curves. So that might mean maybe you have a cardioid and then, some other polar graph, maybe a smaller one, and it would give you the area between them. Don't worry, no volume to look at here. And then length of a curve should look kind of familiar. It's very similar to, we had done length on the Cartesian plane. We had done length with parametrics, and here's length with polar. Now surface area, we'll skip that for now. The formula for that's on 565, but would call that kind of non-essential. What we will do is we will look at a couple problems in class, but what I would encourage you to do before then is, in terms of examples, I would check the book for now. We want to finish up in class with you having the opportunity to work on problems. So, see you then.